Okay, here is the first isomorphism theorem for rings. There are a couple of different versions of this, but the version I'm going to use is given a surjective ring homomorphism from ring R to ring S, the induced map or function f bar from the quotient ring f mod kernel of I to S given by f bar of the left coset A plus I equals f of A is an isomorphism. So a couple of items just to recall for the listener. Okay, recall that the kernel of a homomorphism is the set of elements in R such that f of A equals 0, and this is the 0 in S. Okay, so this is the set of things that map to 0. Also recall that the kernel of f is always an ideal in the domain. In other words, it's a subring. Well, it's non-empty because it has 0. It's closed under subtraction because something mapping to 0 minus something mapping to 0 maps to 0. And it actually has that vacuum property that ideals have. Something mapping to 0 times something not mapping to 0 by the very nature of homomorphisms maps to 0. So this is an ideal. Okay? Since kernel of f is an ideal in R, that means that you get here a quotient ring. Okay, so this is the set of left cosets of the ideal. That's why here you see that A plus I is a left coset of R. It's an element of this quotient ring. Now I need to take an element of this quotient ring and from that produce an element of this ring. Well, it turns out that the element that I want is whatever element f would have taken R to. Now you might say, well, the coset representative that I'm using there is not unique. That's true. You might have A plus I, the left coset represented by A, equal to B plus I, where A and B are totally different things. But the point, the reason that this map is well defined, is because if that's true, then think about this. If that's true, then you have A is equal to B plus, let's say, C for some C in I. Because, of course, B plus 0 is over here, and so B plus 0 is in this set. Sorry, A plus 0 is in this set, so that means A plus 0 can be written as B plus something or other. So we have this right here. Well, if that's the case, then f of A equals f of B plus C, and since f is a homomorphism, that's f of B plus f of C, and what does it mean to be in the ideal, which is the kernel? Well, what it means is that it maps to 0. So if C is in the ideal, which in our case is the kernel of f, and perhaps it would be more illuminating if I actually wrote kernel of f there. That is going to be 0. So if you have two representatives of the same coset, can you see that they map to the same element? And that is well defined. So that is the first isomorphism theorem for rings. Let's sort of think about what that means for a particular example. So here's an example. Actually, in a previous video, I spent some time developing this, but let's think of the ring of lower triangular matrices with entries in R. Let me think of the map from there to R cross R. Now, the reals are ring, the reals are ring, so you get pairwise operations here for everything inside here, multiplying the first quadrant, multiplying the second quadrant. Now, I could give you a map, a function, from R, those particular 2 by 2 matrices, to R cross R, given by f of A0, B, C equals A, comma, A, comma, C. Okay, so hopefully it's not too challenging to see that this is actually a surjective map for any element in my codomain, any AC. I just pick an element A0, say 0C, and it would map to it. So this is a surjective map. And it's also a homomorphism. That might be a little harder to see, but let's see if we can't do a sort of a proof sketch here. F of A0BC plus X0YZ, if those are two elements in the domain, would equal F of A plus X, 0, B plus Y, C plus Z. Well, and where's that going to map to? That's going to map to A plus X, C plus Z, by the definition we gave right there. And then, of course, that you can see is F of A0 BC plus F of X0 YZ. So it's a homomorphism under addition. If you watch the same thing happen under multiplication, you should be convinced that it's homomorphism. X, Y, Z. First job is to do that multiplication. Let's see. So the important thing is that this entry is AX. This entry is XB plus YC. Let me write that a little larger. So AX 0, and this entry is CZ, right? And so the point is that maps to AX comma CZ, and of course AX comma CZ is AC times XZ, which is F of the first component times F of the second component. So A, B, C, X, Y, Z. Okay, so not really a full-fledged proof, but the idea that this is a surjective homomorphism. So the first isomorphism theorem says that F bar goes from R mod the kernel of F to R cross R is an isomorphism. So let's imagine that you don't really know what this quotient ring looks like. You're pretty comfortable with R cross R. You'd like to know what this quotient ring looks like. And there was a previous video where we talked about that quotient ring. But I didn't call it kernel of F. I actually talked about what kernel of F was. Okay, so what is kernel of F? Kernel of F is the set of matrices A0, B, C such that F of A0, B, C equals 0, 0. Right? So what is that set? Well, of course, if you want to think about precisely what the definition of this symbol is, it's the set of A0, BC such that AC equals 0, 0. And so you could actually write this set as the set of elements 0, 0, 0, B, such that B is a real number. Okay, and this is a set that I talked about in the last video. So we have the quotient ring here. I'd like to know what that quotient ring looks like. And the induced homomorphism from here to here proves that elements here look and act exactly like elements there. So when I'm thinking about elements in R mod kernel of F, right? So what would elements there look like? Elements there might look like something like 5, 0, -2, 3 plus kernel of F, right? I could think about that as acting exactly like what F bar of that element looks like. F 0, -2, 3 plus I. Okay, and what is that? That's just 5, 3. So when you're thinking about the elements of the quotient ring, you might as well just think of them as order pairs that are the diagonal. So that's how the isomorphism theorem hopefully helps us to understand something about this ring because we understand something about this ring.